Now let's consider what would be the situation, how we could find the center of mass of an object that's not a collection of point masses like we had here, but it was, for example, like the carpenter's right thing here, like this. So let's just say that it's made of steel. It's an L-shaped object, and it's about 6 inches here and 8 inches here. So let's put the x-axis right here, put the y-axis right here, and this is our 0, 0. And this, let's say, is 6 units, and the thickness is 2 units, and this height is also 2 units, and the length is 8 units. Where's the center of mass of this object? And its uniform thickness. So we've already got an equation for this kind of thing. We could assume that this object is a collection of 2 or 3 objects. So for example, we can break it up from here and say this is object number 1 and this is object number 2. And we'll find the center of mass of this object is somewhere here, and the center of mass of this object is somewhere here, and then they become as if they are 2 point masses, and then we use the previous formula. So the center of mass of this rectangle we know is in the geometric center. For every regular object, the center of mass is in the geometric center. So that point is going to be 2, between 2 and 6, it's going to be 4, and it's 2 inches or 2 units high, so it's going to be 1. This point is going to be 4, 1. And the area, and we still need to find the mass of this. The center of mass of this is going to be in the center, so that's 8, so it's going to be 4 units up and 1 unit here. So it's going to be at 1, 4. X is 1 and Y is 4. Now the mass of M1 of this part is, the mass is going to be the density times the volume, and the volume is going to be the area times the thickness. So it's going to be we don't know the thickness, we don't know the density, but it doesn't really matter. The area in the case of M1 is going to be rho t, I just brought them together. The area is going to be 4 times 2. So it's going to be 8 rho t, that's M1. And M2 is going to be 2 times 8 is 16 rho t. So these are the masses. Now we'll apply the formula. The Axiom is the sum of MIXI over MI, sum of MI. So it's M1, which mass is 8 rho t, and X is 4, and M2 X2, so M2 is 16 rho t, and X is 1. Divided by, we add the two masses, M1 plus M2 is going to be 8 rho t plus 16 rho t. Now this rho t and this rho t can be taken outside, factored out. These can be factored out and they'll just cancel out. So we'll just be left with 8 times 4, 32 plus 16 over 8 plus 16. And these are just the area times the x and y. So we can simply, for a uniform density thickness, we can simply replace the mass with an area, because the thickness and the density will be constant for all. And now we can solve this. So 32 plus 16 is 48 over 24, so that's 2, so x value is 2. And the y center of mass is going to be the area mi yi over mi. So it's going to be m1, which is 8, times y1, which is 1, plus m2, which is 16, and y2 is 4, over 8 plus 16. So it's going to be 8 plus 64 over 24. So we get 64 plus 8, 72 over 24. That's 3. So the center of mass x, y is going to be 2, 3. So in this figure it's going to be 2, and that's 4 is going to be somewhere here. Well, the center mass could have been out in the air also. Okay, so that's how we find the center of mass of connected objects, which are not point masses. We just convert each of them into the equivalent point mass and just say the two masses are here. And if you join a line together, well, that point will lie exactly on that line, closer to this one because this mass was much bigger, and this further from this one because this mass was smaller. Now, this is not the only way to do it. We could have divided it like this, m1 here and m2 here. We would still get the same mass, same center of mass, or we could have divided this into many parts, m1, m2, m3, m4, m5, m6. We would still get the answer over here. Okay, so now let's go to continuous mass distribution. And let's assume that we have our meter stick, or it's a simple rod. It could be a circular rod, and we want to find its center of mass, which we know it's in the middle, but we would like to show that. So here's our y-axis, and here's our x-axis. And we know that, well, in the y, in this case, is simply 0, so we'll just take the xcm is the sum of mi xi over sum of mi, but there's only one mass, so we break this up into a number of parts. So this will be 1, 2, 3, 4, 5, 6, and so on. So if there are n parts, then we go from 1 to n and 1 to n. And then we can just add them up. Now, the more parts we have, the more accurate it becomes, and so we go to the limit when the mi, or in this case, because the m is small, we call this a delta m located at x. So we can write this as xi delta m over the sum of all the delta m's. Now, the sum of all the delta m's will become just the total m. And so before we write that, let's write that this is equal to the sum of xi delta m over m. This becomes the total mass. Now, in the limit, when delta m tends to 0, then this summation xi delta mi over m become the integral of xdm and 1 over m, and the integration is over the entire mass. So we do this for this case, for which we need to know how to get the dm. For that, we define the linear mass density, which is given by the symbol lambda, and that is the mass over length. So it's the mass per unit length, and it's going to be kilograms per meter, or grams per meter, or grams per centimeter. It's the mass per unit length. And therefore, the mass of, if this distance is delta x, then the dm is going to be the lambda delta x. So the delta m is going to be lambda times the delta x, mass per unit length times the length. So it will become mass per unit length times the length, and that becomes just the mass in that little length. So we use the dm as lambda dx, and therefore our center of mass is 1 over m, and the integral is going to be x, and dm is going to be lambda dx. So when the delta becomes a d, it becomes the same here. And the limit for x is x equal to 0, and this is x equals L. So it's from 0 to L. And that becomes 1 over m. The lambda is, if the thickness and the density are all are the same, it's a uniform thickness thing and uniform density, we can take out, the lambda is constant, we can take it out. We'll have x dx, which will be lambda over m, x squared by 2, and the limits are 0 to L. When we substitute the limits, we get lambda over m, it becomes L squared by 2 minus 0. So we just leave that. And now we can simplify that further. The lambda is m over L. We write it as m over L. The m is m, and we have L squared by 2. So the m's will cancel, and one of the L's will cancel, and we just left with L by 2. So the x center of mass, the position of the center of mass is simply L by 2, or right in the middle of this thing, which was more or less evident, but we have shown it to be so. Now let's take a slightly more complicated example, and this would be useful in some of the homework problems that you're going to do. And that is, if we have in the book it's the same problem with a non-uniform density. We'll do it slightly different. We'll say we have a triangle. So we start from here, and let's assume it's a right triangle. So where is the center of mass of this triangle? And its uniform thickness. It's like a sheet metal cut out here, and with uniform thickness, uniform density. So we take this as the x-axis, take this as the y-axis. This is x equal to 0. This is x equals L, so that's the length. And here y is also 0, and here y is h. So this side is h, and this side is L. Now we want to find axiom and ycm. So axiom is going to be 1 over m integral of x dm over the entire surface. So how do we get a dm over here? So we divide this whole thing into little strips, and we consider one such strip over here located at a distance x and a thickness delta x. The height over here is y, and so the dm, or the delta m at this point, not a dm, the delta m is going to be the density times the volume, the density times the area times thickness, and that's, the area is delta x times the height. So it's delta x times the height. Now we do have a little error here, but in the limit when delta x tends to 0, this triangle disappears. And that's the power of calculus, that we can do this. So when we write dm, it becomes 1 over m x, the dm will become rho and dx, y and t. And now the limits will be from x0 to x equals L. But so now we can take out the rho, which is constant, and the t, but the y is not constant. The y keeps on changing as you go along. The x keeps getting bigger. So we need something. We need the y as a function of x, so that we can replace it over here. Now this we know is a straight line, and the equation of a straight line is y equals mx plus c plus b, where m is the slope. So we can, the slope of this line is h over L, so it's h over L x, and the b is, in this case, 0. So the y can be replaced with h over L x, and we'll do that over here. And so the x center of mass is going to be then 1 over m, and we take out the rho and the t, rho and t, and we're left with an x and a y, and the y will be h over L x. That's the y. And so we got the y and the dx. So we can write this as rho t over m, and h over L are also constant. They can be taken out. Integral of x squared dx, which becomes rho t over m h over L x cubed over 3, and the limits were from 0 to L. So when we put 0, we get 0, so it's only the L term, so it's rho t over m h over L L cubed over 3 minus 0. Now that doesn't look very nice, so we need to try to simplify so that it looks somewhat more nicer. So the area of this triangle is half LH. So we have we can have the H and L here, and the mass is going to be area times thickness times rho. So let's rearrange this Axiom, and we get the A, which is L. Let's cancel out one of these L's. So we pick up one of these L's, and we're left with one L. Okay, from these two we got one here and one here. And the H, we take the H, so we got this and we got this, and we divide by 2 and we multiply by 2, so because we need the 2. So half LH becomes the area. We multiply with the thickness, so that's the thickness, we take it over here, and the density, we write it over here. So we are left with m and 3 3m. Now this whole thing is area, thickness, becomes volume times density becomes the mass, so this whole thing cancels with the mass. And we're left with 2 by 3 L. Now, that becomes very nice and simple. So the center of mass is Axiom is 2/3 L. So in a right triangle, the center of mass is 2/3 of L. So that's L, and that's 2/3 of L. You draw a line here, it's somewhere along that line. And because it's a right triangle in the other direction also, it's 1/3. Divide that in 3 parts, so it's 1/3 from here. That's where the center of mass is going to be. I think, yeah, well, the 3 parts are not so equal, but it's going to be 1/3 from here and 1/3 from here, or 2/3 from here and 2/3 from here. That's the center of mass. Okay, so the YCM will be 1/3 of H. Okay, so that's 2/3 because it's starting from the tip, and it's 1/3 because it's not starting from the tip. It's 2/3 from here. Now, the last topic that we'd like to do, well, before we do that, in all problems involving non-uniform density or non-uniform, like not area, which is not a rectangle or a rod or something, in that case, you need to write that equation, and you would always need to first do the dm in terms of x and y, and then the y in terms of some function of x. You must have a function of x to solve it. Now, lastly, we'll just say that a collection of particles will have a center of mass, and if you have a bunch of particles, like a broken up piece of comets like we have sometimes, then as it's moving and it's acted upon by some gravitational force or some other force, so there's some like the sun here and it's pulling it, then this whole thing will behave as it's concentrated here, and if this center of mass follows a path, some particles will go above, some may go below, but the center of mass will follow that trajectory. Or in other words, if you fire a gun and the bullet goes like this, so now you fire another gun, but this time it has these little shots in it, so they are like, they will spread out as they go further, they'll spread out, but at any point their center of mass will follow that particular curve. Or if you have a firework and you shoot the firework up and it follows a curve, then and it blows up here, one part goes here, another part goes here, well, the center of mass of these two must remain on that line. As it falls and this falls, the center of mass of these two must remain on that line. So the center of mass keeps following the same trajectory, whether the particles break up or they don't, or they move around. If one particle moves a little bit more this way, another one would have to move a little bit the other way, so the center of mass follows the same line that it would have if this were just one solid piece. Okay, so we stop here in this chapter.